Thank you, Gary. I hope you can all see my slides. It's a real pleasure to talk to you all about these general issues. So I want to bring us back, try to get some perspective to one of the greatest heroes of cognitive science, which is David Marr, the neuroscientist and vision researcher. David Marr, who died in 1980 at the age of 35. And in his brief, brilliant career, he did many things, but I think today what he's most known for is the three-level hypothesis, which is that any information processing system must be understood at three levels, sort of a computational theory level about the problem, and breaking down into algorithms and hardware implementation. So the computational theory level is what I want you to really focus on. So what is the goal of the computation? That's what we look at in computational theory. What are the purposes? Why is it appropriate to compute certain things rather than other things? Whereas next level down, the middle level, is how would that be done? Which representations and which algorithms would be used? And finally, the lower level is, again, how, but how physically could it be done? So David Marr liked to emphasize the computational theory level. He thought it was the most important and at the same time, the most neglected. And I think it's still true. It's true in neuroscience that we are missing sort of a high level understanding of the goal and the purposes of the overall mind. It's also true in artificial intelligence, but perhaps more surprisingly in AI, but there's really very little computational theory in Marr's sense in AI. So for example, in AI textbooks, they will often decline to define the problem of intelligence. They will say it's something like getting machines to do things, whatever it is that people do. They won't really explain what it is. And the big ideas and the controversies are mostly at the middle level, and they're not at the computational theory level. So we just heard Louise Lamb talk about integration of neural approaches and symbolic approaches. Well, this is a controversy. It's a focus of the last debate. But it is only about, it's not about a computational theory, it's not about the problem, it's about how you achieve something as if we understood already what it is we were trying to do. It's important always to understand the problem before you approach the solution. And other ideas, production rules, Bayes updating, subsumption, gradient descent, dynamical system theory, all these are hows, they're not whats. They don't characterize the overall problem. So then that brings me to my thesis, that reinforcement learning is the first computational theory of intelligence. Reinforcement learning is explicit about the goal, about the whats and the whys. So according to reinforcement learning, the goal is to maximize an arbitrary reward signal. And to this end, the agent has to compute a policy, a value function, and a generative model. And each of these contributes in a clear way to maximizing reward. And each is a clear what. The value function, for example, is a function from states to a prediction of the future reward. And we know how that can really improve the speed of learning and be used in more cognitive things in conjunction with the model, with the world model as well. So it would be good to have more work at this computational theory level and reinforcement learning. It would be good to have other candidate computational theories. So we might think of other ones like the compression theory of mind, or homeostasis, predictive coding, the Bayesian inference approach. All these can be made more complete and clear. I don't think they rise yet to a level of a specification of the overall problem of intelligence. So as it stands now, I think AI really needs an agreed upon computational theory of intelligence, and maybe all cognitive science needs an agreed upon computational theory of intelligence, and reinforcement learning is the standout candidate for playing this role in our science. Thank you very much.
Is it